we're using pointers. We got our main.
Very crooked.
All right. To indicate we have a pointer, all we gotta do is use a star. And that means that variable takes an address, right? Rather than a value. All pointers take addresses. We have our RAM. We have our RAM. We call this a stack. Maybe I put too many. So, when we have our RAM, and we declare an integer, the operating system uses this is the number, and this, the next line, it's a pointer to a number. So yes.
Pointers are still like variable with the type and
Yeah, what's the type?
it's integer data type.
No, the data type is a pointer to an integer. It means only whole addresses, right? So an address that holds an address. So in here, a number can take any number, right? So when I do that, the operating system goes to the address of inum, which is address 1000, and just puts the number 5. Right? So what's the value of pointer number? We don't know. It's not been assigned yet. So basically, it says this address must hold, or this value. Can I do this? Can I do that?
No.
Can I do this?
No,
Why not?
because it starts with the star.
Anyone?
Because it only takes an address.
Well, that is if it's this, right?
Oh, sure.
But if I do this,
Put the 10 in the address.
so what will happen if I write a program like this? It says, whatever address that is, put the value 10. What is the value of pointer number? We don't know. So no, you will get an error. But if I do this, before I assign it, then now this no longer has a question mark. It has an address. Right? And now this will work. Now what this is going to do says, look at the address where pointer number is. There's 1,000, go there and change. So in essence, I change the other variables, right? The I number, right? Rather than the pointer. But then let's say I have another number. So I'm gonna write it here. So in this order, if I execute this order, another number still don't know what it has, right? But then later on here, now pointer number changes the value from 1,000 to 1,064. Then I can do this. And maybe I can do if I do this is very straightforward, right? So now this goes to 15. And if I say well, this line print. It'll print 15. And if I do this, or will this one print?
The address of that?
Yeah, it will print 1,064, right? So, if instead of an integer, I also add a double, I'm just gonna put a double. So a double means twice the block. So I'm gonna have double here, a double, and this is 64 bits. So it's using 2 blocks, right? So the computer, when it runs, replaces the name of the variables with the address, right? You know that. So what address will it replace here? It'll use whatever a double starts, right? So the computer will replace this one with 1096. So if at any point we do something like the computer is gonna say, go to that address, right? And write in here the number in that whole section. That was a double. But if I use a pointer to a double, when I declare that, how much memory do I allocate? I only allocate 1 block, right? It's 32-bit. Because assuming I have a 32-bit operating system, that's all it allocated. The double itself is this much memory. But a pointer to a double is the same size as a pointer to an integer, right? They just hold an address. And they just hold the address where that variable begins. So this variable, for instance, the I number starts at 1000. So if I look at address 1020, it's still part of the number, right? If I look at the address 1128, it's part of the double. Double starts at 1096, right? So if I were to do this one, will just hold the address of that double, right? You follow? That's pretty much what pointers do. What if I want more? What if somehow I could allocate more RAM, more than just 2 blocks, maybe allocate 4. So I got those 4. So basically, each variable, there's no breaks in the memory addresses, right? I know a number an int is 32-bit, I start at 1000, and I grab 32 bits, right? If I have a double is 64 bits, I start 1096, and I grab 64 bits. So the thing is, the trick is to have contiguous amount of memory when you have a variable. So let's say this is an int, this is another int, I want 4 ints together. But I want them together. Assuming that I could make them stay all those ints, 4 ints together, I just have to figure out where's the address of my first int, right? It's like a list of numbers. Well, it's not really a list, that's a different definition, but if I declare 4 ints at once, like in the whole line, chances are the computer is going to give it to me all together, right? But what if I have 1,000 ints? Do I declare 1,000 ints so they're that becomes really tedious, right? For instance, what's the student population here? 30,000, 50,000, who knows, right? Let's assume there are 30,000. And I have a variable for each student ID, an int. Trying to declare all of them, it'll be really painful. So instead, we're gonna make an array. We're gonna say, I want 1,000 ints. I want 1,000,000 ints, whatever. So the way it works, let me erase this.
Yeah.
Look at it. Needs to be clean. So the way is where do we start? And an array, there's a condition for the array, and that is everything has to stay together. So all the variables I declare, if I need 1,000 ints, all those ints have to be together physically in the memory. I'll show you how this works. Let's erase this, I don't need it. So the way this works, assuming that we could make them all stay together, the array will. All we need to know is where that array begins. So if I have 10 ints, all I need to know is the address of the first int, right? And I know the next 32 bits is the next int, and the next 32 bits is the third int, and so on. Oh, gotta wait until it dries. Sorry. So, what happens is we have a base. And our base okay, let's say we want ints. And then we gotta declare the student IDs. And I want 10 of you. So I'm gonna use square brackets. And this square bracket is the signal to tell the computer this is an array of 10 numbers. So what the computer is going to do is going to allocate 10 ints. So an int is 32 bits, right? And what it's going to do is declare a pointer to an int. And I need 32. I'm sorry, I need 10 times 32. That means I need 320, right? So it's going to give me all this contiguously. So I went and brought 320 bits together in memory, and it returned the address where those 320 bits begin. I could do something like this. And I can say pointer because this is just like a pointer. Instead of pointing to one int, it's pointing to 10 ints. That's all it is. So, when we look at this student IDs, and we have this square bracket, we have a number in here. It's ID square bracket. So this student ID, we call it this is a base address. What do you mean? Well, student ID starts its address 1000. What goes inside here, there's a number, has a few names. The book we're using calls it a subscript. Some other parts of the book call it an index. Other textbooks call them an offset. So we know the computer counts when we have a number, let's say 2 to the 8, we have a byte and it's unsigned. We say if we have 2 to the 8, it's 256 numbers, right? And the numbers we can accommodate are 0 to 255 because we count 0 as a number. We always count 0 as a number. So if we start counting our elements for an array, we have 10. We can start saying this is element 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Right? Because 0 counted. So this number is the index. And that's what the number goes in here. So what the computer does, let's say I want to store in the first element the number 10. Can I do this? No, because this is a pointer, right? It's just, instead of pointing to one int, it's pointing to 10 ints. So I can't do that. But because this is an array, I gotta use, what index number is that? 0. I can do that. So now the computer will put the 10 here. So if I want to put it in the fourth element, the fourth element will be index 3, right? Because 0 counts. And let's say I want to put the number 25. So the fourth element here, that's you, that. So the way the computer does it is we have this base address. And this offset, it becomes a multiplier. So you say, how big is an int? It's 32 bits, right? We all know that. So this number, this offset, is going to multiply it. So if I say 3 times 32, that will be 96, right? And this is my base address. The base address was 0x, sorry, plus. So now the address is going to be, that's what the computer does when it does this line and goes to that line. Follow? So this one works because it still multiplies 0 times 32 and 0, so it just uses the base address. That's how it assigns each element of the array. So I have an array, and the only 2 indexes I have a set are 0 and 3, so the rest are just garbage, right? We don't know what they have. So if I want to initialize, let's say, all the values, all the elements of the array to a number 10, for instance. How could I do that? Use the loop, right? Let me erase, what? Can you see from, but yeah.
Sorry, when pointer was assigned with student ID.
These are equivalent.
Yeah, what they're doing.
Arrays are just pointers.
Oh, okay.
So I could do something like this. Go make a for loop. Actually, I'm going to initialize them to maybe 0. So if I do that, I have a loop, and I can just set them all to zeros. And of course, it'll erase the ones I had before. So, have you ever in your computer, when you're searching for a file, you're like, I don't remember the name of the file, and you just put partial name on the search box, and the computer comes and says, index locations might, if you don't have an index location, might be slower. You never seen that? So when you, I don't know if you're dedicated or not when you study, but do you buy sometimes those little white cards? Yeah.
Index card?
They call index cards, right? You know why they call index cards? So, let's say we are in 1970 and then you don't have a computer, you don't have Google. Can't imagine the world without Google, right? But you want to go to the library. Yeah, you have to have a Rolodex. And the Rolodex had what? Index card, right? So you have this, and I want you to understand this concept because this is how the file system works. And we're going to talk about files after we're done with arrays. So, in those index cards, it has basic information about the book. You know, maybe you have the author, the title, maybe category, and you have the location of where that book is, right? So you just go to the front desk, look at the Rolodex, find the index card, and then you, oh, it's an aisle, whatever. Then you go to the aisle on the shelf and you find your book. Well, the computer works the same way. Computer has arrays all over the place. And it has an array of your files. And in that array, it holds the beginning address of your file. So what a computer does is when you search for a file name, you just look at this Rolodex. And then pulls that index card. And then it goes to the physical address of the hard drive and pulls the file for you. Now, do you ever go to your cell phone provider and see what calls you made? But you're cool, right? You could go and say, oh, give me the calls for, and you put a day span and it shows up. So let's say you have, I hate AT&T, but let's say you have AT&T. How many calls do you think they have per day?
9.
9 million maybe, right? So if you put a date span, imagine how long it'll take to search every number, every call. That will be a monumental task, right? So how do they do it? That like you press enter and then report comes up. Even your bank transactions, you can do that. It's because they're using indexes. They're using an array. And the arrays are useful if and only if they are sorted. So, how does this work? Well, if I tell you, if you think of a number between 1 and 1,000,000 and I'll guess it in 20 tries, will you believe me? Well, the computer can. Well, let's do 1 to 1,000 in 10 tries, okay? All right. Just do you think of one? Don't tell me.
For me.
Yeah, sure. So if I'll ask you, my first try, I just go on and say, is it 512? Then I'll ask you, is it greater or less?
Less.
Then my second try will be, is it 256?
No.
Then ask you, is it greater or less?
Less.
Right? Next one's 128. Is that the number?
Less.
Jeez, you thought 9 maybe?
No, it could die.
All right, so same thing, less or higher.
Less.
All right, so I keep going. 5 is 32.
That's it.
All right. No, she said it was 32.
I should have picked the number not divisible by 2.
It's fine. I still catch it in the same try.
Hit 31.
All right, then if it was 31, I'll ask you if it's less. You say yes.
And it's great.
So I will go 16,
Higher.
and then it will be higher. And I go in between. That will be, what is it?
24.
Yeah, 24, right? And that will be higher, right?
Yeah.
So the 8th will be
28.
between those two. That is 8, so it's 28.
28.
And then you say it's higher, so between 28 and 32.
30. Yeah.
It's 30. And my 10th try is 31.
Okay.
Dude.
I mean, I will use so if I have an array of 1,000 numbers, if I have to go check each one, I might get lucky, right, and find it in the first try. Or I'd be really, really unlucky, like me playing the lotto, I'll be in the last position. I use all 1,000 numbers. So in average, if my array is random, it's not sorted, on average, basically, I will take half of the number of elements of the array to figure out where it is. Right? Maybe I get lucky, I get the first one. Very unlucky, it'll be the last one. But on average, will be, if I have 1,000 elements, will be 500 tries, right? So, in an unsorted array, the number of tries to find something, an array of n elements will be n over 2, right? They call this, when you go to data structures, they call it a big O. I don't know why. Big O number, maybe. So the big O of an unsorted array is n over 2. You remember at the beginning of the semester we talk about algorithms and we say what was the floor and what was the ceiling. Like we say,
Oh, yeah.
if we say the ceiling, we just round it up to the next number. So if my array is sorted, like when I ask you think of a number, I assume the array was sorted, then it will be just a logarithm base 2. I'm sorry, the ceiling of n. So if I have 1,000 elements, if n is 1,000, this will be 10. So the ceiling log base 2 of n equals 10 because 2 to the 10 is 1,024. So I could have gone all the way 1,024 and then be the same result. So if I say the ceiling base 2 of a million is just 20. So you ask, where else will you use pointers or pass by reference? If you imagine that library, what you have in that index card is very limited. You don't have the whole book, right? You just have paragraph at the most. And those things that are in that card, that index card, we call it index fields. So if you want to search by title, you could search in the index card, right? If you want to search by author, you could search in the index card. You want to search on word hello on page 10 of every book, you have to go search the entire library, right? Because the whole book is not indexed. It's just certain fields. That's why you see it in your computer when you're searching for a file. If it's not in an index location, it'll take longer. Does it make sense? So, we're going to talk about arrays a lot today. And next class, hopefully we'll finish it in 2, maybe 3. Questions so far? Yeah? Alright, let's take 10 minutes.